One laser passes through one narrow slit, but the screen does not show one narrow line. It shows a broad central band, dark gaps, and much weaker side bands. Why does one opening make a whole pattern? Diffraction is the spreading of a wave after it passes through a gap or around an edge. It occurs at every gap and edge. The question is not whether diffraction happens, but how much. Let plane wavefronts meet a gap of width A. When A is many wavelengths wide, the angular spread is small. In this near aperture construction, much of the front remains nearly plane, and curvature is most visible near the edges. As A approaches lambda, the outgoing wave spreads through a larger angle. The key comparison is A over lambda. Diffraction is especially noticeable when the gap width and wavelength are comparable. This is why sound can spread through a doorway more noticeably than visible light. A sound wavelength can be similar to the doorway width. Visible light wavelengths are far smaller. Light still diffracts, but through an angle too small to notice here. Because the medium does not change at the gap, frequency, wave speed, and wavelength remain unchanged. Only the directions and amplitude distribution change. Huygens construction models how a wavefront propagates. In a uniform medium, treat every point on the front as a source of a secondary wavelet. After the same interval, every wavelet has the same radius. The new wavefront is the forward envelope tangent to them. Without a barrier, that envelope is another plane wavefront. Now insert a barrier. The covered part cannot contribute to the transmitted wave, while every exposed point across the gap does. A wide gap retains a long, nearly straight middle, with curvature near the edges. A narrow gap leaves a much more strongly curved outgoing front. Replace the gap with a small obstacle. Wavelets on either side continue and spread into the region behind it. The same construction represents diffraction through a slit and around an obstacle. That construction shows how the front spreads, but the detailed bright and dark bands need superposition. Reset the optical slit so it is still many wavelengths wide, and place the screen far away. Contributions from the whole continuous aperture overlap. Straight ahead, they arrive in phase and form the central maximum. At the first dark minimum, pair each contribution from one half of the aperture with one from half a slit width away. Each pair arrives half a cycle out of step and cancels. At other particular directions, there is also complete cancellation. Between them, cancellation is incomplete and weak side maxima remain. The slit is not just two edge sources. Now read the monochromatic pattern. Monochromatic means one wavelength. The central maximum is the brightest and the broadest. In the small angle far field pattern shown, the central lobe, measured between its first minima, is about twice the minimum to minimum width of a neighbouring side lobe. The side lobe peaks decrease rapidly. The first reaches only a few % of the central peak. Keep the wavelength and screen distance fixed, then make the slit narrower. The first minima move outwards, so the central maximum becomes wider. Less light passes through, so at unchanged exposure, the total transmitted light and the on-axis peak both fall. This does not mean the narrower pattern is fainter at every angle. Now keep the slit and screen fixed and increase the wavelength. The pattern becomes wider again, so red spreads farther than blue. With white light, every wavelength component peaks on the central axis, so the center is white, although the central lobes have different widths. For corresponding minima and side maxima, violet lies closer to the axis and red farther away. The weak side colors overlap and wash out. They do not form perfect repeated rainbow stripes. Diffraction occurs at every gap and edge and becomes especially noticeable when gap width and wavelength are comparable. Huygens wavelets explain the spreading front. Superposition across the continuous aperture explains the bright and dark pattern. A narrower slit or a longer wavelength produces a wider central maximum. Next, we will use two slits to develop interference and Young's double slit pattern.